This is me, Nova Meg, and I'm about to go on a job interview. As you've probably noticed by now, I have a huge coffee stain on my white blouse. So professional. I'm probably thinking about a million different ways I could have avoided this situation. What if I hadn't been drinking coffee? What if I had stayed up so late? What if I had been staying? There are countless decisions that all played a role into leading up to this one awkward situation. A change in any of these seemingly insignificant factors would have completely altered the outcome of my situation. I've therefore created a chaotic system.
So what is chaos? Chaos is the inherent unpredictability in the behavior of a complex system. The two things that make a system chaotic are nonlinearity and the butterfly effect. A nonlinear system is a system in which the input is not proportional to the output of that system. And the butterfly effect is a property of chaotic systems in which small changes in the initial conditions of that system can lead to large-scale and unpredictable effects in the future state of that system.
If I blow this balloon up twice in the same way and let it go in the same place, wouldn't we expect the trajectories to be similar? That is, however, not the case. The balloon is therefore an example of a chaotic system. It is nonlinear since when I let go, it did not travel in a straight line. It also exemplifies the butterfly effect since, despite having very similar initial conditions, the final trajectory was completely different. This means the balloon's paths were greatly affected by slight changes in the initial conditions.
So how chaotic is a chaotic system?
Edward Lorenz, the founder of chaos theory, was able to simplify weather into these three nonlinear equations. After discovering that weather is a chaotic system, Lorenz graphed these equations onto a 3D plane. We would probably expect the results of plugging three values into a chaotic system to be a disorderly mess. This is, however, not the case. Plugging in the different values creates a graph that is surprisingly orderly for such an unpredictable system. Lorenz named this shape a strange attractor, and this specific one became known as the Lorenz attractor. Strange attractors provide an underlying order to chaotic systems.
Imagine that you're watching a car drive on a racetrack. Close your eyes for a few seconds and try to guess the exact position of the car at the moment you open your eyes. Impossible, right? There are infinite possible places for that car to be. You do, however, know one thing. The car will be somewhere on that track. The car is a chaotic system, and the track is a strange attractor. It provides a much-needed order and structure behind the chaos of our universe.
Let's now go back to this awkward situation and explain how it's a chaotic system. This situation was the outcome of millions of decisions made in my brain earlier. Brainwaves, unlike heartbeats and respiration, are an unpredictable chaotic system, and when graphed in a 3D plane, create a complex but orderly strange attractor.
Knowing the underlying order of a chaotic system brings us one step closer into being able to predict the outcome of that system. Chaos theory, however, doesn't only apply to weather, brainwaves, and the path of balloons. Oscillations in chemical reactions, the pattern of smoke, defibrillations of the heart, and many, many more occurrences in the natural world are all chaotic systems with strange attractors. With further study into chaos theory, we may be able to one day make the unpredictable predictable.